have kind of control of the early universe before BBN. So we know that at temperatures higher than TBBN, so higher than, say, a few MeVs, the energy density of the universe, so the Hubble expansion was dominated by radiation, by standard model radiation. So okay, standard model radiation, let me emphasize this. Yes, so Hubble is dominated by standard radiation and adiabatic, meaning that the entropy of the standard model is conserved, which means basically that, which implies that T goes like 1 over the scale factor. T, the temperature of the standard model, temperature of photons. So this is basically what is known as standard cosmology. So the idea is that we know that, that this is satisfied after BBN. The idea of standard cosmology is that we extrapolate this, so to the highest temperatures of the universe. We don't know, so we assume that after reheating, after cosmic reheating, inflationary reheating, we have this that is fulfilled. Another kind of common assumption is we take this reheating to be at very high temperatures, so we don't know what the scale of reheating. It has to be higher than the BBN, right? So we also assume that the reheating happens, cosmic reheating, let me put, happens at very high temperatures, T reheat, I don't know, very high, much higher than TBBN. So I don't know, T reheat typical as it's model, of course, it's completely model dependent, but I don't say T reheat 10 to the 10 GeVs or so. I mean, of course, it's completely model dependent, but just want to see that it's a big number. And we typically assume that the reheating is instantaneous. Right? So, and we'll see what happens if we have non-standard cosmic evolutions. So that's a bit what we started studying yesterday. In particular, one particularly well-motivated case is the early matter domination. And remember, the idea is very simple. So we know that's radiation, so relativistic particles. So energy density scales like 1 over A power 4. So it's like 1 over the volume plus redshift. While the matter scales only like 1 over A cube. So 1 over the volume. So that means that radiation is diluted faster, much faster than matter. And therefore, even if you start with a subdominant matter component, so non-relativistic particles, it eventually could dominate if it's long-lived enough. So we discussed, for instance, you have a heavy guy, a heavy moduli, a heavy right-hand neutrino, or these heavy particles coming from in God extensions. If they are long-lived enough, and with lifetimes, say of the order of seconds, because we want to recuperate, to recover standard cosmology. So if their lifetime is long enough, so seconds or so, we can naturally have early matter domination, right? And I show you the thing that was the very last thing I showed you last time. So this evolution, and we discussed of the energy density times A power 4, and the temperature of the standard model bath times A, so A is the scale factor, as a function of A. So let me redo this. This is kind of complicated because I'm taking into account the variation of degrees of freedom. So let me do a more simple, so exactly the same, but simple picture. So as a function of the scale factor, I'm plotting here the energy density times A4. I choose there. And why A4? Because if I make energy density times A4, radiation energy density yes, is constant, free radiation. So we have these 3 scales. So I called this A a equality, here a critical, and here a end, or a reheating, what did I choose, end. Okay, so the idea is that I have this matter component that scales like 1 over a cubed, its energy density, times a4 times, yes, so it's something that will grow linearly, like this. And at some point it will decay, right? Something like this. So linear increase because I'm multiplying by a power 4, and it decays. So it's matter that decays. So this is energy density of matter, right? And now I will draw the one of radiation. So it's something here constant because it's a4 times over 1 a4. It will keep going like this. So something like this and something like this. This is basically what we see there. So we have an era here where it's dominated by, the Hubble expansion rate is dominated by matter. So this is really early matter domination. Here, we recover radiation domination, and the early universe is radiation domination. Yes, so for me, equality and n correspond to the beginning and the end of the early matter dominated era. So there's another scale here, which I call critical, which correspond to, I mean, before that, we have like an adiabatic expansion, meaning that even this guy is dominating, but it's effectively not decaying. So it's not effectively injecting entropy in the radiation. So radiation still behaves like free radiation. And there's an era, non-adiabatic, where you really start to feel the effect of the decay. So the entropy injection, that means that radiation is not scaling as free radiation because we have a source term. And the source term is that we are assuming that this guy phi, okay, this matter that I will call phi, is decaying into standard model particles. Yep. So we have entropy injection, we have a non-adiabatic era, and we see that. So radiation is not scaling as free radiation. Why? Because we have a source term. So that's basically the plot on the left. And this can be translated into temperature. So temperature of the standard model bath. Because remember that by construction, rho of radiation, it goes like T power 4. I can put this exact formula. It's pi squared over 30. G star, remember the G star counts the number of relativistic degrees of freedom times T to the 4. So if we know T energy density, we can extract the temperature because these photons, I mean, they're always in equilibrium. Times T times A. So we expect for free radiation to be constant. T times A is constant. So let me put again these 3 lines here. These 3 scales, A equality, A critical, and A end. So, and again, here is early matter domination, radiation domination, and radiation domination. So here is constant, we have an increase here, and constant again. Here it goes like, T goes like 1 over A, and this can be solved analytically, and this here in this non-adiabatic era, T, let me put here, T goes like 1 over A, 3 over 8. 3 over 8 here, this area here. So it's radiation with a source term. We also wrote the Boltzmann equation for these guys. So N, remember, phi is the non-relativistic guy, yes? So N is the number density. So we can keep track of the evolution of the number density. So the N phi over the T plus 3H and phi. H Hubble expansion rate, I know it will have 2 components, right? 2 contributions. And this 3 means really correspond to the equation of state. So it's a proxy of the equation of state, meaning that it's matter so that it will evolve like 1 over a cube equal to minus gamma and phi, and this gamma corresponds to the decay width of this guy. So we want this to be small enough because we want, after all, to have a long lifetime, right? So that's Boltzmann. This gives us the evolution of number density of phi, right? We can also write the evolution of the radiation energy density for the standard model, rho radiation, for h rho r, and 4 again is 4 because exactly because of this. So we know that energy density scale like the volume, but also there's a redshift factor, so it's radiation. But it's not free radiation, it has a source, which is basically this thing. Is the energy, and this part corresponds to the energy density of phi. So it's not relativistic, so its energy density is number density times mass. These two equations are coupled because of the source term, but also because the Friedman equation. So Hubble has two contributions, rho radiation and rho of phi, and rho 5 mass phi and phi over 3 m Planck reduced Planck square. So you guys, for instance, can play and solve this set of coupled equations. You will get that, yes, if you take into account the change of degrees of freedom, or solve it analytically and find this kind of behavior. So in particular, you can find that this scales like 3 over 8 in the case where they have a matter and where this guy is has a constant decay width. Okay? Yeah. Good. We can also compute, for instance, or estimate the temperature at which this guy decays, phi decays. So remember, we can compare the expansion rate with the term coming from the collision, if you want, or the decay term. So if we compare h with gamma, yes, so gamma is constant, t depends on the end. We can extract, or can we estimate the moment, the temperature at which this guy decays. So the temperature equivalent to this corresponding to a end, so the moment where the guy decays, by equating these two when the Hubble expansion rate is equal to the decay width. And from here you can estimate the end. So the end square is basically 3 over pi yeah. So just to have you an idea of the scale there. But of course, you can also just do it all numerically, solving these things. Okay, the important thing is that, remember, we're thinking about the cosmology because if you want to estimate the dark matter number density, we have to have control both on the particle physics, read the models, so if it's WIMP, FIMP, Cannibal, Elder, Axion, whatever, but also the cosmology, right? So remember that for WIMPs, for instance, or for SIMS, Elder, so all these thermal and non-thermal process, we wrote the Boltzmann equation for the dark matter. And that's exactly what we wrote. So N is the number density of dark matter, 3H, 3 because it's non-relativistic at freeze out. Okay, no, sorry, because it's number density always goes like H, like 3, sorry. Sigma V, N squared minus N equilibrium square. Now what you have to do is to solve exactly the same Boltzmann equation, but with a different background. And why a different background? Because we have an extra component, which eventually dominates the total energy density of the universe, so this guy phi. So actually what you have to do, if we care about dark matter, is to solve a system of 3 Boltzmann equations, one for the dark matter number density, one for the energy density of radiation, and one for the number density of phi. So it's 3 Boltzmann equations coupled because of Hubble and because of this guy. Yes? So here, let me emphasize that I'm assuming that the guy phi is only decaying into standard model. You expect it to decay also into dark matter with a branching ratio, big or small. But we're assuming that we have only this, so the branching ratio into standard model is exactly 1, right? That's why I'm not having here an extra source. That we'll take into account in a couple of minutes. So we say that this equation is kind of not particularly useful because here you're having a time dependence. However, all these quantities, okay, the sigma v, the n equilibrium, Hubble, typical depends on, I mean, we understand them as a function of temperature. So what we did before was to redefine this, just a change of variable, define this y like n over s, and x like m over t. Remember, that's exactly the kind of plot I was always showing you. The evolution of the comoving dark matter number density, a function of the inverse of temperature. However, remember, this kind of change of variable makes completely sense in the case, in the case of standard cosmology, where you have an adiabatic evolution of the universe and where you have radiation domination, standard model radiation domination. So that's what we did, but we cannot do this. Here, in this case, it's a very bad idea. However, that which is always guaranteed, which is always a good idea, is to define, so like capital N, like n times a cube. Number density times n cube. And why does it make sense? Because we know that if there's no interaction, if there's no collision term, n, remember, is non-relativistic, so n goes like 1 over a cube. So this is completely general. You can always make this change of variables. Yeah. So instead of small n number density as a function of temperature, of time, sorry, you can rewrite this, and this is completely general, like this quantity. So number density, basically the number of particles, right? This is number density times a cube. A cube is basically the volume. And the scale factor. And this is trivial, right? We just make just this change of variable, the n, the a, and what I get is a 4 and this is always valid. This is valid when you have, I mean, it's independent of who is dominating the energy density, and if you have or not entropy injection, right? So here, from here to here, I'm just making this change of variable, right? So we have the evolution of capital N, which is basically the number of dark matter particles, as a function of the scale factor. Yeah, you can do that. Of course, at some point you want to recover the dependence on the temperature, but you're solving the temperature here, because you solve the evolution of radiation, and from radiation you can extract the temperature, because photons are always in equilibrium, right? Okay, now what's the effect in particular in the case where we have an early matter domination? So there are 2 effects. One is that we are increasing Hubble, right? And why are we increasing Hubble? Just because we have an extra component. Yeah. So if I remove this, it will be smaller, right? So I'm putting an extra component. So we have more energy density, so the universe will expand faster. So this guy H will be bigger. That means that the freeze out will occur earlier. Two effects. Bigger H will be larger. And remember, we estimate the freeze out by comparing H with gamma. But gamma, remember, that was n equilibrium times sigma v. if this guy is bigger, for a constant cross-section, you have to increase an equilibrium. And equilibrium has this Boltzmann suppression, so you have to go to smaller temperatures. So the first effect is that you have early freeze out, and therefore, if you freeze out, remember, something like this, right? So you want to increase, if you freeze out earlier, you're overproducing dark matter, right? If you freeze out earlier. So you tend to increase the dark matter abundance. Yeah, just because you're adding extra matter, so you're having a larger value of Hubble. That's one effect. However, this one is subdominant because we're also having an entropy injection, right? We're also producing dark matter particles, and remember that what we know is this omega h square, right? And this basically is the energy density stored in dark matter over the total energy density of the standard model. So if you want the critical density, if you're injecting entropy, what we'll do is that we're diluting, so we're creating more photons, we're diluting dark matter with respect to the photons. So we'll have a dilution because of entropy injection. Entropy injection. And this implies dark matter dilution. So we have two effects that go in the opposite direction. An increase in Hubble tends to increase the dark matter abundance. However, the entropy injection, because of the decay of the guy that is dominating the energy density, tends to dilute. So two opposite effects. However, this one dominates and typically and by far. Yeah. So at the end, in this early matter domination, you have a dilution. So that means that you have to kind of overproduce dark matter. Why I'm having this? Okay, yes, exactly the same plot I have shown you basically 100 million times. So the case of WIMPs, for instance, in a standard cosmology. So the same boring behavior. Now, what happens if we instead of the freeze out in radiation? So basically, if you are in this era, what happens if you start to freeze out to produce dark matter here, here, or here? So here I will show you some evolution. So it's exactly the equivalent of this. So, but solving this full set of Boltzmann equations for dark matter, number density of phi, and radiation. So it's exactly the same equations now with different moments. Okay. So for instance, let's start with this plot on the upper left corner. So that corresponds, okay, here I'm showing you the same vertical line. So first, the red is the equality, the critical, and end. So early matter domination is between equality and end. And this vertical line corresponds to the moment of the freeze out. So dark matter is freezing out actually here during radiation domination, but before the early matter domination. So it's a very early decoupling, right? So what you see is that you have the freeze out, so you reach a plateau, right? This part is exactly the same as before. So in this part, the universe is dominated by phi, but there's basically no entropy. It's the adiabatic process. There's no effective dilution. I don't see this thing. Rogerio. Then you enter the non-adiabatic period, so where you have the effective decay. So you are diluting dark matter, and therefore you can see that the yield goes down, right?
Just a question. So X freeze out, you said that it's for me looks very much the same. No, always 20.
Yes.
So what do you mean by early freeze out?
early freeze out means, no, I was thinking about the period. So it happens, what I meant is, it happens before the onset of the early matter domination era. Yes, but of course, here, this freeze out happened exactly in radiation because it happened before the equality. So the freeze out is exactly the same. So 20, what we have seen. Exactly, no change at all. The only difference is that you have like dilution. Dilution is maximal because you're filling the whole period of the non-adiabatic period. Yeah, so that first plot corresponds to freeze out here. So let's put one. The second is this one, the right, top right. So it's very similar. However, the big difference is that, well, it's different to see in the plot, is that the freeze out happens when the universe is dominated by phi. So it's here. So we have domination by phi. However, you are not feeling the decays, right? So there's no entropy dilution. So but it is very similar, right? I mean, you cannot see the difference. So you have a very, here really it's an early decay. It's an early freeze out because of this, right? H is bigger than in radiation domination, so the freeze out is slightly earlier. And therefore, you have the suppression when you have the entropy injection. So this case number 2. Case number 3 is here. So you have freeze out during early matter domination, and on top of that, you're feeling the entropy injection. So here you can see, so it freezes out here, but then it doesn't reach the plateau, right? Here, after freeze out, you have the plateau, here and here. Here you don't, because you're producing, so dark matter is out of chemical equilibrium. However, you're feeling the suppression, the Boltzmann suppression, the entropy injection, sorry. So you reach the plateau only well after you don't have injection anymore. Okay, so this is exactly the same WIMPs, the same, I mean, neutralino dark matter, could it be? Just that we're playing with the cosmology. And in particular, we are allowing this early matter domination era. Yes? No, sorry. No, this guy is the one that triggering the early matter domination. So it's unstable, so we wanted to decay into standard model particles. So yes, so let me put here dark matter, right? So I have at least, I mean, you have on top of the standard model, you have say 2 new states, dark matter and phi, which is the one triggering the early matter domination. Yeah, so right-hand neutrino, very heavy with a lifetime long enough. Exactly. Here is really a WIMP, so the kinetic decoupling happened much later, so the temperatures are exactly the same. But of course, you can do the same exercise with elders or with cannibals. Yeah, and we will do. Yeah. Yes. Our favorite model, singlet scalar dark matter. I showed you this plot yesterday, I think. So again, so remember, it's exactly the same model. So we have singlet scalar with a Higgs portal. So lambda HAs is the Higgs portal, so the coupling between dark matter and Higgs as a function of the dark matter. And we studied these 2 solutions. So masses in the GV to TV ballpark in couplings order 1, this corresponds to the WIMP solution. While this line here, so much broader mass band and couplings very suppressed, say 10 to the -11 or so, correspond to the pure FIMP solution. So WIMP on top and SIMPs here. So we say that in between these 2 lines, we have a dark matter overproduction. Here on top and here below is underproduction. So not enough, too much, and not enough in radiation domination. So let's do exactly the same exercise in this framework where we have an early matter domination and see what happened. So it's a very crowded plot. So here I assume Tn to be, so the end of the early matter domination to be few MEVs because I just want to avoid problems with BBN, right? So this corresponds to the maximal effect of early matter domination. And these gray lines correspond to different values of T0, and I change the notation, sorry, is the equality. Yeah, so these have basically two free parameters, the temperature at which this phi, the early matter domination, starts, and the end. So N is few MEVs. This T0, these contours correspond to increasing values of T0 or T equality, so the onset of the early matter domination. So we say that there were two effects, but the dilution was the dominant. So this region here between the two thick black lines correspond to the region where in radiation domination we have an overabundance. Now we have an early matter domination, we can fit the observations. And again, these lines correspond to different cosmological scenarios. So several comments. For instance, you can see this dotted line corresponds to the border between thermal on top and non-thermal at the bottom. So meaning that above this line, dark matter reaches equilibrium, both chemical, or in particular chemical equilibrium, meaning that dark matter is thermally, dark matter is a WIMP, right? So on top of this, we have a WIMP. Below, we have a FIMP, right? So non-thermal production. So you can see that before we have like two disconnected solutions. However, now there's a continuum solution, and you can go naturally from WIMPs to FIMPs in these early matter dominations, right? So we are just increasing by a lot the parameter space where this very simple singlet scalar dark matter model can fit observations. Yes. So we cannot reach this part. Basically, these correspond to, okay, yes. Here the freeze out happens at temperatures smaller than T end. So basically, you're completely insensitive. It's basically the freeze out happening here. So after the recovery of radiation domination. So if it happens here, so if you imagine the early matter domination happened at very early stages, so you're completely insensitive. So you can have an early matter domination, fine, but you don't feel the effect at all. Yes, thanks. Okay, my questions or comments? Okay, okay, I did that for early matter dominations, but I could in principle do the same exercise, taking more exotic cases. For instance, this guy could have I'm assuming it's a constant. You could have a more difficult, more involved behavior. It could depend on the field, for instance. We can also imagine the case where this guy has a different equation of state. I don't know, like kination or other scenarios. But I mean, that's the idea, that we have some freedom, we can play with the cosmological evolutions, early cosmological evolution of the universe. So here I was playing with this piece, right? Now we can also imagine that we can play with reheating. So remember, so Kfir, I think he discussed about, I'm not sure, in the lectures about reheating, but remember, we in the early universe, we need an epoch of exponentially fast expansion of the universe, so we need inflation, but after inflation, the universe is basically dominated by the inflaton. The universe is basically empty with respect to standard model particles. So we have to create, maybe for the first time, all the standard model particles, the standard model bath. And that era is what we call reheating, or the heating, the cosmological heating of the universe. So we don't know, I mean, the uncertainties are maximal there. We don't know how reheating occurs. We can imagine that reheating happens via, let me put this. Latour. So we can imagine that reheating could proceed via the decay of the inflaton. So before phi was a heavy guy, any non-relativistic particle, we can imagine, now I will use the same notation, but now I'm thinking that phi is the inflaton. So the reheating could proceed via this kind of reactions. So decay of the inflaton of a non-relativistic inflaton. We can imagine that after inflation, the inflaton is oscillating in a quadratic potential, so a equation of state 0. So it scales like non-relativistic matter, and it could decay into standard model particles. So it's very similar as the scenario discussed previously. However, that's not the only possibility. So the inflaton, for instance, could oscillate in a quartic potential, so with the energy density that scales more like radiation. Or you can also imagine that the reheating doesn't goes through any decays, but through annihilations. But in principle, reheating is much more complicated, right? So you can, in general, it could be dominated by non-perturbative process. We can have preheating, so it's a mess. But just let's study the simplest case, where during reheating, or the reheating proceeds via the perturbative decay of a non-relativistic inflaton into a couple of standard model particles. So at this point, is very similar to the early matter domination. So I can write the equations of, and are basic, I don't have because they're here. Yeah, so in this case, where the inflaton, sorry, if we assume that the inflaton is non-relativistic, during inflation, so that the potential of the inflaton is basically m squared phi squared. During reheating, and assuming that reheating happens through this kind of process, and it's dominated by this kind of processes, what we have to do is basically solve the same set of Boltzmann equations. And why? Because we're assuming that it's non-relativistic, so it has energy density. Okay, no, this for number density has to be 3. That the energy density is mass times number density, and that it proceeds via the decay of the perturbative decay of the inflatons into standard model particles. So the Boltzmann equation will exactly be the same. Yeah? And exactly the same for dark matter. So you just don't have to copy it again because it's exactly the same. However, the initial conditions are different. So this part is the same. So for instance, I can show you the evolution of the background. So I'm taking, for now, I'm forgetting about dark matter. So I'm just taking the evolution of the background. And evolution of the background, I mean the evolution of the inflaton. Now the phi is the inflaton of the reheaton, so the particle driving the reheating in blue. And the evolution of the standard model energy density in black. So, right, so these, okay, and now I have only to scale, so the beginning of reheating and the end of reheating. End of reheating correspond to the onset of radiation domination. So during inflation, I have only the inflaton. So during inflation, the question, I mean, is constant energy density, is cosmological constant if you want. And there's basically no standard model, so it starts to decay during reheating and it starts to produce the standard model. So you have basically a very sharp increase in temperature. You're populating the standard model. You're producing a standard model bath. right? During reheating, you have a coexistence between inflatons and standard model radiation. However, it's still dominated by inflatons. And at some point, you have the equality, right? So you have, that's what we call the reheating temperature. So the moment, the first moment where standard model radiation starts to dominate the Hubble expansion rate. So there will be inflation, reheating, and radiation dominated phase. So several comments. So one, okay, now here's exactly the same plot, but for the temperature. So again, I can extract the temperature because remember, rho, so the energy density in radiation is basically T power 4. So I'm showing here the equivalent plot for the temperature as a function of the scale factor. Yes. So during inflation, basically I have no standard model, so temperature 0, whatever that means. So you have a very fast increase, very fast thermalization, and you reach a temperature which I call Tmax, because it's the maximal temperature reached by the standard model plasma, which is typically higher, it could be order of magnitude higher than T reheat, right? Which T reheat is the correspond to the onset of radiation domination, right? So after reheating, so when the universe is dominated by, so this is what we saw before. So A, temperature, so we have fast increase, something like this. This is A reheating, and this is what I call the A end, whatever. So after reheating, the radiation is free. It's free radiation. It goes like 1/A. However, during reheating, in this particular scenario, the temperature scales like 1/A and 3/8, exactly the same as before. So again, you can solve this analytically or fully numerically, solving this set of Boltzmann equations.
I have a question. So the
Sure.
only inputs for this is the energy density in the inflaton in the beginning and the inflaton width. Is that correct? The mass of?
Exactly, yes. So yes, so you need, no, here you don't need the mass of the inflaton. So you need the initial Hubble expansion rate, right? And you have bound for that. I mean, we haven't observed B mode, we haven't observed gravitational waves, primordial gravitational waves. So this guy has to be smaller than, I think it's that 2 × 10⁻⁵ Planck mass. Yes. And the other constraint is that you want T reheat again to be higher than TBBN, so whatever, few MeVs. Yes, so that's it because, okay, so the initial condition for phi comes from here, right? The initial condition from radiation is 0. And that's it. The only thing is gamma. But gamma is somehow related to this, because from gamma is what the question I wrote here, right? So if you know the reheating temperature, an upper bound, you have a lower bound on gamma phi. Yeah, please.
Are you defining the temperature of the standard model by the entropy density of the standard model? Then I guess I'm just surprised why it's rising so fast. I would have thought that it rises on the same time scale as the inflaton decay. Or is that the inflaton decay? Is that the time scale for that?
Yeah. So here I'm assuming instantaneous thermalization. So I'm really extracting. Yes,
because I would have thought that somehow the inflaton decay is controlling the width of that. You know, the reheat temperature versus the end of inflation.
So the inflaton width is controlling this moment, this scale.
Oh, I think I forgot about M Planck. The point is it's the same time scale, but that time scale that's the A, right? And so that's very, no, I'm sorry, I'm still confused. I'll let you talk. I'm confused, and you'll try to unconfuse me, and then I'll be quiet.
Okay, no. So you can estimate this moment, the moment when basically the inflaton has completely decayed, by comparing Hubble with H, Hubble with gamma. Sorry. Yes. So comparing this, you can extract what I'm calling T reheat. Yes. However, it's true. What I'm kind of cheating is I'm assuming that the instantaneous thermalization of the standard model And at these temperatures, I think is not a completely good idea. So I'm assuming that you always have that the energy density is basically this is basically T power 4, always. Which so instantaneous thermalization. You have to be careful here. For instance, I'm assuming that the temperature is 0, so I don't know exactly what T exactly equal to 0 is. So at the beginning, you expect this to be non-thermal, so have in particular very high modes, and not really a thermal distribution. Yeah. So energy density standard model comes from the decay of what is it? Of phi. So at the beginning of standard model particle have exactly half of the mass of the inflaton. Good. Yeah.
Exactly when like we have the standard model when the black line spontaneously started, but then you said it's decaying at the reheating temperature later. I didn't understand how who is creating that standard model. What's happening? Like is thermalization? I don't understand this part. Before the reheating, you said there's instantaneous thermalization. You don't have any standard
Yeah.
model particles, and then you have.
Instantaneous thermalization, I mean that you create a black body spectrum, right? So they have this distribution.
You are creating that after inflation.
Yeah. So what's the question?
Yeah, I just don't understand. I think it's a simple question. Like I don't understand the physics of that. So it then inflation and then.
So after inflation, the inflaton starts to decay.
So the inflaton decays, but this is not the reheating temperature where the inflaton decays.
No, the reheating is when standard mode starts to dominate.
Okay. So
Yeah.
part is when the inflaton decays, and then the other reheating is when the standard model dominates.
Exactly.
Okay,
Yes.
now I
So
understand.
the reheat, maybe reheating temperature is end of reheating temperature.
Okay.
Sorry.
Because
Yes.
the reheating,
So
I think, is the moment where the inflaton is decaying.
yeah, but it decays in a finite. I mean, it takes some time, right? So
So this
if
is
you
the
want, for
end
me,
of
the reheating is between what they call
okay.
T max and T reheat. So T reheat is really the end. So
This
the
is
onset
end.
of radiation domination.
Okay, now I understand.
Yes. Sorry.
Okay,
Yes. So reheating is not instantaneous, and I'm making all this big deal is because, in principle, dark matter could have been produced, even if it's standard WIMP, it could have been produced during reheating. And in this particular, this simplistic version of reheating. And I have this, exactly the same model as before, right? So the singlet scalar dark matter model, the same Higgs portal, mass. This part is WIMPs. This part is FIMS. Sorry. So this blue, I think is blue dotted line correspond to the border between thermal and non-thermal production. So above is thermal production, so I will call it a WIMP or a WIMP-like guy. Below is non-thermal, so it's like a FIMP. Here you have a single free parameter, which is, okay, I'm assuming the maximal scale of inflation, so I'm cheating a bit. And I'm taking I'm varying T reheat, so the end of the reheating, right? So it has to be a temperature higher than few MeVs. So 4 MeVs, TeVs, 10 to the 6, 9, and 12. And the message is exactly the same, right? So we had before that all this region between WIMPs and FIMS were gave rise to an overproduction in radiation domination. However, if we allow the reheating temperature to be small, right, to be low, we have this very important entropy injection, and all this parameter space becomes available again, right? And we can also see that we can have a continuous transition between FIMS, for instance, if you take this, and WIMPs. So it's not a disconnected solution, but we have a continuous connection between one and the other. Yeah.
Question. So, are you assuming this picture that the inflaton does not decay directly into dark matter?
Yes, I'm
Yeah.
assuming it's exactly 0, which is, I will make a comment. I mean, if, for instance, in this scenario, it makes no sense. So if you want, I'm assuming the branching ratio to be very subdominant. Particularly, I'm taking here to be exactly 0. Yes, so the problem is that my original plan was to talk about, in this last lecture, about detection. However, you can see maybe tomorrow, next week actually, another school. So I just have one plot where I put some experimental constraints, and it's this one. So it's exactly the same as before. Look, just that I put on top, I overlay this projection for an actual bounds from direct detection, indirect detection, and what? Direct, indirect, actual projection, and an LHC, right? So this part here corresponds from data from the LHC, so the invisible decay of the Higgs. So in this particular model, the Higgs can decay into 2 dark matter particles, S and S. So it's an invisible decay, so dark Higgs into a couple of dark matter particles. So it's ruling out all this orange region. So you can see that basically dark matter lighter than half of the Higgs mass is already excluded in the standard WIMPs. So but it's so interesting that we are already ruling out a chunk of parameter space of FIMPs. So in this model, we're already testing, already excluding part of the parameter space favored by the FIMP mechanism with a low reheating temperature. So with LHC, we're not only testing WIMP, but also FIMS. And the same applies, for instance, in this like bluish region, which correspond to, I think this is the xenon n-ton, so direct detection, and this corresponds to projection in direct detection. And again, you can see that we're already probing parameter space favored by both the FIMP and WIMP production in low reheating scenarios. And also you can see that basically the bulk of this parameter of this model is in strong tension in the WIMP scenario in standard cosmologies because of very strong experimental limits. Okay. No, some benchmark that we choose, but yeah, I'm not showing you. But it's equivalent. The idea was to show the evolution. So it's basically these curves. Yeah. Okay. Now, do you remember this plot? So I was showing you. So xk, okay, x prime freeze out corresponds to the freeze out temperature, and I will define this x as mass over the temperature. So this corresponds to the moment where you have the kinetic decoupling and the chemical decoupling and kinetic decoupling. So remember, this is the freeze out of number changing interactions, where this is like really elastic interactions. So xk is important, the kinetic, remember, is important because it guarantees that the temperatures of the two sectors are exactly the same. So we saw this plot a couple of days ago. These lines here correspond to the scenario when dark matter is a WIMP or a SIMP. These parts here, kind of horizontal, correspond to the Elder scenario, and here when they become vertical again, correspond to the cannibal dark matter scenario. So we studied this, we gave a lot of details in the case of radiation domination. So we show you the equivalent of this plot when we allow the reheating temperature to be in this scenario, this simplistic scenario, when we allow it to be low, in particular lower than the typical scales, so the freeze-out temperature or the kinetic freeze-out temperature. So this 3 plot is exactly what I'm showing you. So forget this alpha. This alpha refers to this 3/8. So it's exactly this picture. So what I'm doing here is I'm variating x reheating, and x reheating is basically the same x like here. So the dark matter mass over reheating temperature. So large X reheating means small, low reheating temperature. So let's start by here, by these plots. So no, but this one is 0.2. So what you can see, so I'm decreasing the reheating temperature, this one, then this one, and then this one. So you can see several, okay, and this dashed line here corresponds to the border between radiation, so when the freeze out happening in radiation domination or in reheating. So these lines here, here as well, and here basically all. So here you can see, for instance, compare this one, so radiation domination, with this one when you have the extreme low reheating temperature. So you can see, for instance, that you can find, so this part here corresponds to WIMP, so we can have, for a given mass, so the different texture of the lines correspond to different masses. So the solid line here corresponds to 1 TeV, while the dashed line corresponds to 1 GeV. So, and remember that this part here, when xk is much larger than the x prime freeze out, corresponds to the WIMP scenario. So you can see for a given mass, 2 solutions of WIMP happen. So that means that for a given mass, you can have 2 couplings that give rise to WIMPs in a given standard cosmology, which is something that we never find in the radiation domination. So you have a multiple solution for the WIMP and for the FIMP, for the SIMP case, sorry, in the case of low reheating temperatures. Also, we see that when xk is smaller than 1, we don't have the cannibal solution anymore. Remember that when xk was smaller than 1, we have the vertical scaling of this line. Oops, no. Here. This was the cannibal, right? So when xk was smaller than 1, the solution became vertical because we were reaching the cannibal scenario. Here is not the case anymore, right? So even when xk is smaller than 1, we don't have the cannibal, or if you want, we have the cannibal, but they are not independent of the value of xk, of the kinetic decoupling anymore. Yes, we have a very rich phenomenology now in the case where we allow reheating temperatures to be much smaller. So let me accelerate a little bit. So I would say that we are assuming in the previous scenario when you have early matter domination, or in this case, we are assuming that the inflaton or the guy driving the early matter domination to decay only into standard model. However, in general, this guy will decay into all the particles. In particular, we can assume that there's a branching ratio could be small into, or not, into dark matter. And in particular, we cannot avoid the decay into dark matter, because even if you don't have direct coupling, so phi, we're assuming that we have phi into standard model particles. So even if we assume that this is the only decay that happened at 3 level, in this scenario, we can also close this loop. We can also have a loop of standard model particles and then dark matter, right? So you can always, in this scenario, when we assume that we have interaction between the standard model and dark matter, so we can also induce decays into dark matter via loops. So this guy could be very suppressed, right? This loop suppressed, but it's definitely non-zero. And that's interesting because it's like a minimalistic approach. So in this last half an hour, I will discuss like, how we'll call it, minimalistic. I don't know. So this was one possibility. And I have, no. Here, we can assume, for instance, this kind of decays, right? So we can assume, for instance, that inflaton decays into dark matter. So I changed the notation, sorry. Dark matter is now this chi. So again, as I told you, this could have a direct coupling or loop induced. But just assume that there's a branching ratio into dark matter. So phi goes to dark matter with a branching ratio. Yes. Big or small, I don't know, but this is non-zero. So I can slightly modify these equations. I can add, yes, okay, I will reuse this if I find the equations. Yes. So this will be exactly the same. So this will now be the total decay width. So the total meaning the decay into standard model and dark matter. However, only a fraction will decay into radiation, will be injected in radiation. So I will put blah, blah. I will put here the changes in blue. Basically, it's 1 minus this branching ratio. And I have here, so let's assume this cross-section is exactly 0. For now, just focus on decay where there's no direct contact between dark matter and standard model. So you have here plus branching ratio, gamma phi, and phi. So let's study this case where dark matter is only produced through decays, to two-body decays, perturbative decays of the inflaton. Right? So this part is exactly the same. The inflaton is decaying into what? Into a bit into the dark matter with a branching ratio BR, and the rest into radiation. And this can be solved analytically. You can do it because you know how this guy scales. You can put it here and compute the dark matter number density. And what I did for you. Yes, so assuming again the instantaneous, for instance, instantaneous decay of the inflaton, I would say that the comoving number density is basically the number density at T reheat. Yes, when this guy decays. And as you will see, it's very simple. It's 3/2 G star, so the degrees of freedom contributing to the energy density over G star S, the one for entropy. T reheat, mass of the inflaton, and BR. So super simple. So it depends on the reheating temperature, on the mass of the inflaton, and the branching ratio. And that means that this branching ratio has to be equal if, or smaller if you don't want to overcloud the universe. Yes, I'm just pulling these terms. So the branching ratio, if you want to fit the observation, the branching ratio has to be exactly equal to this part here. If you don't want to overclose it, it has to be smaller than this. So it will depend on the mass, T reheat, mass of the inflaton, T reheat, mass of dark matter. And this Y0M, remember, is the 25%. This is, what was it? 10 to minus 11 GeVs. So this is a number. So just to put some numbers, so for instance, typical numbers of T reheat or and mass of the inflaton, well, typicals, well motivated by some prejudice, right? So if you, for instance, in Starobinsky inflation, you have the mass of the inflaton. What happened? It's a sociological argument, right? So we like to put the mass of the inflaton at around 10 to the 13 GeV, and T reheat at, say, 10 to the 10 GeVs. So this is a typical number that appear in Starobinsky inflation if you have alpha attractors. But I mean, there's no really put any number right here. It has to be, yeah. I think it's between 10 to the 15 and 10 to the 4. and mass of the inflaton, yeah, I don't know. But okay, we follow, this is trendy to use these numbers, basically, so sociological thing. So in this case, the branching ratio has to be smaller. I'm just plugging these numbers, huh? To 10 to the minus 9. There's no room. 10 to the minus 9, 100, for a dark matter particle of 100 GeVs. And this is impressive, right? So this is a very small number. So it's very easy to produce the whole or even to overclose the universe, even with a super small branching ratio. So we have to be careful with this. And remember, this particular...
Just a question. Do you have to assume that this dark matter does not thermalize after the decay of the inflaton in the history of the universe? Is that or not necessarily?
That it thermalize, no chemical thermalization. Kinetic could be,
Kinetic could
but
be,
not
no
chemical.
Okay.
Yes. Yeah, so because you don't, this is true if all dark matter particles are produced via this mechanism, right? If you have chemical equilibrium, that means that you have in equilibrium number changing interactions, so the result will be different. Okay, yeah, that's a good point. This is true without chemical, chemical equilibrium. Yes.
So the temperature will be different from the universe. The temperature.
Here, yes, but here basically the temperature at production, the temperature, I mean, the typical energy is the mass of the inflaton over 2, and then it redshifts because it's not interacting at all.
Yeah, actually they are monochromatic first. I mean, they only have one momentum.
Yeah.
But then they can.
Yes, if you assume that they decay instantaneously, they are all monochromatic.
Right.
If not, they're monochromatic at production, but that you have the redshift and they're produced at different epochs on the universe. Yeah. Yeah. So yeah, I'm assuming there's no chemical equilibrium reached here. You can take that into account, of course, and it will be a little bit more complicated, but that's it. So yes, important, and this is very important in the case of non-thermal dark matter. Remember we discussed about FIMS, non-thermal dark matter. We said it was depend on the initial conditions, and we are assuming that the original population of dark matter was always 0 because there's no reason, right? But however, this is an example where we have to take into account initial population. This will be kind of one like initial condition for the FIMP mechanism, right? So there's a population produced by other mechanisms, for instance, by the decay of the inflaton. And you have to take that into account in non-thermal process or in general in process that depends, that are sensitive to initial conditions. Yes. Questions? Yes.
That you have in the beginning due to these numbers. But you also need to take into account like gravitational particle production during inflation, for example. It would be like the same order of magnitude or some. What?
Now we'll talk about gravitational production à la carte. Your desires are order. No, not yet. Your desire will be orders. Yeah, so but basically they emphasize before going to the gravitational production that you can have, so we discussed like the FAIR process, decay of the inflaton into a pair of dark matter particles, but you can also have scatterings of inflatons right? For instance, if you allow trilinear coupling of inflatons. But even if you don't have trilinear couplings, for instance, you can have these kinds of scatterings, right? So it's exactly the same coupling here. So inflaton with two dark matter, so decay. Inflaton to two dark matter, you can see here, so T-channel exchange of to T-channel production. Of course, if it's dominant or not, that's another question, right? But these processes are there. And we can also imagine other processes. You can imagine, like this one. So where the inflaton here acts as a mediator. So these two processes here have to happen during reheating, because during reheating the universe is dominated by inflatons. Here we don't see inflatons roaming around. However, the inflatons could also be a virtual, so the portal between the standard model, so Higgses and dark matter. So you can also imagine this kind of process. You can compute that. So of course, if you take the inflaton to be 10 to the 13, as in that case, this will be slightly suppressed. But in the other scenarios where you have a light inflaton, you can imagine this process to be there, maybe dominant. And now, you can also imagine other kind of mediators. You can, for instance, a graviton. So you can imagine that the graviton could mediate the dark matter production if you have scattering of inflatons, right, during reheating, or even you have scattering of standard model particles now at present or in the early universe after reheating, when the universe was dominated by standard model radiation. Of course, you can always compute this. You expect this to be completely subdominant because it's gravity, and gravity is weak. But in principle, taking, of course, perturbative, you can compute these processes, right? These are not, I mean, you have all the tools, right, from the course of QFT. We are not used to this. I mean, it's kind of a little bit more complicated because it's a spin 2, so polarizations are kind of but you have all the tools. So you know that this guy is a spin 2, is massless, that it couples, the coupling is proportional to the stress energy tensor. The coupling is like 1 over the Planck mass, but there's no mystery there. So for instance, you can compute, and it's interesting because it's exactly an example of the UV films. Remember we discussed the UV films? And we can compute the number density, so we can solve the surprise, the same Boltzmann equation for dark matter and number density of dark matter equal to some gamma, so rate density. And for instance, in this case where we have standard model scattering, so the one on the bottom, so a standard scattering of standard model particles mediated by this graviton. So, okay, let's put 1. So standard model scattering. So really standard model, exactly the one below. Dark matter. You can compute this, gamma, and it's very simple. Of course, the computation is horrible, but then you expect to be proportional to m Planck power 4. So you have two couplings in the amplitude square m Planck to the 4, and on top, of course, if you assume that the dark matter, if you assume the mass, if you neglect the masses, so at very high temperatures, I mean, the only option is here to have T power 8. Yes, this guy has dimension 4, so it has to be over 8. Let me put here alpha, and there's a coefficient. So alpha is like 10 to the minus 4. Yes, alpha is equal to, or is more or less, 2 10 to the minus 4 or 5, 10 to the minus 4, depending on the spin, right? For scalar dark matter, and if it's a Majorana fermion. And let me emphasize that there's basically no free parameters, right? So, okay, you have the mass of the dark matter and the spin, but the rest, the mediator is completely fixed, the couplings are completely fixed, there are not really many parameters to play with. So we can analytically solve this Boltzmann equation. You can analytically solve, so it makes sense, remember, to translate this equation to the n over the a, I don't remember, equal to blah, 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 blah. So the same as before. And this you can analytically solve, or numerically if you prefer. And I will give you the answer. This is basically 45, this alpha. I don't know why I'm giving you all the details. And it has a dependence on T reheat over M Planck. If the mass, for small values of the mass, small for, if the dark matter mass is smaller, much smaller than T reheat, or basically the same thing, but here is T reheat 7. So the details are not very important. What is important here is that basically there are no free couplings, so no free parameters, but the mass. So alpha is basically, it's a constant that depends on the spin. It will depend on M Planck, of course, is gravity, and T reheat. This is an example of the UV freezing. So UV FIMS. So you have a strong dependence on the initial condition, meaning T reheat, so the reheating details. And also, so if the dark matter is very light with respect to T reheat, you have a production in the radiation domination era, because the initial state is standard model, so we have plenty of standard model during radiation. However, if the mass is heavier than T reheat, you have a production deep during reheating. So this will be production after reheating, and this will be production during reheating. And I have not much time, but I have a plot here. So two scenarios: scalar dark matter on the left, fermionic Majorana dark matter in the right. So I'm showing you the required reheating temperature as a function of the dark matter mass if we want to fulfill to produce the whole dark matter abundance. And for now, let's look at the red curve here. So this corresponds to exactly this scenario. So production of dark matter, gravitational production of dark matter through standard model scattering, assuming just this process. So it's this one. So we can see the two regimes: light dark matter, light with respect to T reheat, and heavy dark matter with respect to T reheat. So yes, what I want to show here is basically it's an example of what we saw of the UV freezing. So freezing that really is produced during reheating or just after reheating, right? And it's interesting to see that, this is a kind of irreducible process, right? So there's no freedom. That has to be there. This could be dominant or not. Of course, there are other gravitational production mechanisms. I'm not even saying that this is a dominant one. I just want to give you an example of an irreducible gravitational process. And again, even if you're doing films, you have to take into account this, right? These are examples. I mean, I show you that you cannot start with films, or in general, if you take into account non-thermal dark matter with an initial population to be exactly 0. It could be small, it could be subdominant, but here you have examples where you see that you cannot get rid of this, you cannot get rid of, right?
Well, why cannot go above 10 to the 14 with the blue lines? The mass of the dark matter cannot go above.
Momental. Okay, now I'm talking. Now here is only the other. You don't know if it's red or black. The standard model is what I'm discussing. Yes, this one.
Okay.
Only this one. This is scattering of standard model. But I can, if you want, I can discuss about the other one. And I will, yes. So that was the first part. So you have like a couple of minutes more. So the other, this was standard model, scattering of standard model particles. So this diagram here. Now let's see this, this one. So scattering of inflatons, so during reheating. And it's basically the same thing, right? So the initial state is slightly different. So we produce dark matter from inflatons, right? The same kind of Boltzmann equation, we just have to change the collision operator. And I will just write here just for you to have an idea of what this beast look like. So the energy density of the inflaton square over 1024 pi and Planck power 4, and 1 kinematical factor mass of the inflaton. This can be rewritten as a horrible number, something, okay, proportional to, I don't want to write, okay, alpha, I have already used alpha. Number to some number, T power 16, M Planck power 4, T reheat power 8, and this same kinematical factor. And the message is exactly the same, very strong temperature dependence. I mean, the temperature of standard model plasma, but also the reheating temperature. So what I was saying, I was calling the initial conditions. And you can solve that, again, both analytically and numerically, and these are your blue lines. So it will depend, so it will really produce during reheating, because after all, during reheating is the only moment where you have inflaton dominations. So it will depend not only on T reheat when you solve, but also on this T max. Remember that T max, if you want, is the beginning of the reheating, so the maximal temperature reached by the thermal plasma. So these three lines correspond to different ratios, T max over T reheat, 10, 100, and 1,000. And this kinematic, this sharp cut here is just kinematic. So it corresponds basically to the mass of the inflaton. So dark matter cannot be heavier than the inflaton, and that's why you have this strong kinematical, which is basically encoded here in these Fs. They're, expressions. Okay, for the scale and the fermionic case, but you have the same. So the message is the same. So if you want to compute non-thermal processes, like in particular FIMS, and you guys may be very interested, you have to be very careful with the initial condition, in particular with this irreducible process. And I just gave you three examples. So the decay of the inflaton, and also gravitational scattering of standard model particles and inflatons. And I think that was, yes, that was all that I want to tell you. Look, 10:30.
Thank you, Nicolás. So questions for Nicolás? Yes, just a sec. He's faster than me.
So just to be clear, this reheating, it's exactly the same mechanism, right? You're only considering that now you can scatter via a graviton, but in both these cases you have the inflaton field that is producing a reheating, right?
Yeah, it's not produced during reheating, it's just decaying or annihilating.
Yes,
For
I mean,
instance,
yes.
here is an example of where you can have reheating through annihilations, right? So
Okay.
annihilation of inflatons into, you can put here standard model particles, so you can have in these two reheating, so transfer of the energy density stored in the inflatons to standard model via annihilation.
Okay.
But
No,
yes.
actually, my question was if this was an extension of the previous things that we saw.
No, well, it's not even an extension. It's exactly the same framework. I was only assuming that I have this coupling, inflaton to standard model and to dark matter.
And now dark matter. Okay.
Exactly. And maybe you don't, as I said, maybe you don't have the trilinear, so the contact interaction between dark matter and inflaton, but you can produce it also at loop level. So maybe even though you have it at tree level, you can produce it at loop level. Yeah.
Okay. Thank you.
More questions?
Anna.
In this last scenario, this process is being produced. It's happening during deheating or during inflation.
Well, the point is that this kind of product during inflation will be typically subdominant because you have the exponential expansion of the universe. So, of course, you can have that, but it will be completely subdominant. Typical production during inflation, not always, but it's typically diluted. Yeah.
Okay. So this is pretty much a nightmare scenario, right? Because this is the minimum thing, only coupled to gravity, and you can produce the right relic abundance just by this.
Yeah, it's nightmare, but it's the only thing that we have for granted, right?
Yes.
Dark matter interacts gravitational. The other things are like wishful thinking.
Yes.
So we wanted to have order 1 coupling, that to be order GV, but
Yeah. Okay. Any other questions for Nicolás? All right. So let's thank Nicolás for this very nice set of lectures.
thank you.
Everything you ever wanted to know about dark matter, right? Everything